Hey, hi everyone. My name is Praveen Kumar. I'm the founder of towardsmachinelearning.org. I have Ansh with us who will be presenting you today on GANs. So maybe I'll quickly take answers from you. Like I see many of you have joined our sessions in past as well. Any new member in the session today? Just say new and the old. Maybe that should be enough. The new members in the session today who are joining us today for the first time, just say new in the chat window, and the people who have joined us in the past, even for a single live session, please say old or whatever you feel, okay, but not new. Okay, yeah, Sanat Lakshmi, I have been seeing you consistently. Thank you so much for joining us regularly. That too. Yes, Ajay, I'll send the attendance link. So this is the something new that we are trying this time. So instead of taking the attendance in the Google form, we'll take the attendance, on the social media platforms. So you guys will not have to, waste a lot of time in filling up lots of details. So you just have to say joining or not joining. That's all. So I have mentioned attendance link on 3 platforms. First is the LinkedIn, then Facebook, then the Instagram. So someone who does not have the LinkedIn account, please mark your attendance on the Facebook if you have the Facebook account. If you do not have the Facebook account also, please mark your attendance on the Instagram if you have the Instagram. And if you do not have any of these three, neither LinkedIn nor Facebook nor Instagram, then please create one. It's high time that you come on LinkedIn at least. Okay. Okay, I see. Like I see a mix of population. If you are new as well, Rahul is attending us for the first time. Same with the Ajay as well. All right, all right. So could you please mention your profile as well? If you are a college student, please say college name and the year and the stream that you are pursuing your degree into. If you are a working professional, please say the company name and the years of work X that you carry. Can we do that exercise? People who are from college, please. Okay, Rahul is okay. Awesome. Rahul has got 4+ years of work. Could you please mention the designation as well, Rahul? When I say designation, means the profile that you are working into, whether software engineer, full stack developer, data scientist. So we know the our audience, so it helps us to explain the concepts accordingly. Could others also cast their vote in the chat window? Thank you, Nandi. You have attended us earlier also, I believe. Okay. Could others also marketing executive, data analyst? Awesome. Great. Shubham from IIT Hyderabad, second year MTech students. Thank you so much, Shubham, for joining us. All right. So without further ado, maybe I'll hand it over to Ansh to take it forward from here and start the session.
Hi guys, am I audible to you? Please comment down in the chat section. Okay. Okay, cool. So in this today's session, we are going to talk about the introduction to generative adversarial networks. Okay. So we will start with my brief introduction. I am Ansnahar. I am currently pursuing my BTech from IIIT Jabalpur. My major interest lies in the field of deep learning and computer vision. So today's session is all about the generative adversarial networks. So in short, we call it as GANs. So GANs are one of the advanced topic in our deep learning, and a lot of research is going on in this field. It is one of the hottest research topic nowadays. And apart from this, it has a lot of industrial applications. Various companies are using GANs for different purposes. We will see all of them. So let's walk through the table of the content we have for the today's session. So I have divided the complete session into 3 parts. In the first part, we are mainly going to talk about the word adversarial. So we will see what are adversarial examples, what are adversarial attacks, and what are the defenses, and why these adversarial example exist, and all those things. And in a second part, we are going to talk about the generative models. So GANs are one of the generative models. Okay. So we will see the applications of GANs, case study of different type of GANs, and at the last we will see the implementation of DC GAN. Okay. So since it is the advanced topic in a deep learning, so we have the prerequisite as well. You should aware of the basics of the deep learning, neural network, forward propagation, backward propagation, CNN, optimizers, and all those things, and a little bit of image processing, basics of the computer vision. Okay. So before moving ahead, I would like to ask you how many of you are familiar with GANs. So please comment yes if you are familiar with GANs, or no if it is new to you. Okay. Can we have some more responses? Okay, let's move forward. No more VA. Okay. Okay. So let's move forward. So the first thing is adversarial examples. So what are the adversarial examples? So basically, adversarial examples are the input to a machine learning model that is designed to fool your network. Okay, they are like the optical illusions for the machine. So, but the thing is how we can fool a neural network. So suppose you have a very good network that is basically used for a classification purpose, for the that is used for classifying the animals and humans. Okay, so what you do, you take the human image and you add some kind of noise in it. Okay, and after adding the noise, you feed this image to your network, and your network is classifying it as an animal. So that is how we are fooling the network. They are just like the optical illusions for the machine. We will see some of the examples in the next slide. So even optical illusion exists for the human being also. In this current slide, if you focus on the center of these structures, you will find them moving. So that's the same case with the adversarial learning. So we have adversarial examples for our neural network as well, and we have a explanation for the same, why they exist. Okay. So in this slide, you can see we have a image of cat that is classified as 92% cat. Okay, so we have a very good network that is classifying it as a 92% cat. Okay, so what we have done, we have added some kind of noise in it, in the image. So this is how an image looks like. Okay, wait a second. So this is how an image looks like after adding some kind of noise, and the same image is classified as iguana. Although for a human being, this is a cat, we can we can say that yes, it's a cat, but for our network, it is the network is classifying it as an iguana. So that is how an iguana looks like. Okay, so you can find us check the similarity between these two. Okay, so moving forward, we have another adversarial example. So in which a panda, which is our network classified it as a 57.7% confidence that it is a panda, and we added some kind of noise in it, and the same this is how it looks, and same panda is classified as given. Okay, yeah, you can see. So the source for the same is this reference paper. Okay. So, and this is another adversarial example. So in which a dog is classified as ostrich. So sometimes the modification in a real image can be very slight that even a human can't observe it. Like in this case, you can see, yes, we have added some kind of noise in this cat image and it is like distorted one. Okay. Here you can figure out by your human eyes. But here human being cannot say whether we have added some kind of noise in it. Okay. So so that's the thing. Sometimes the modification can be very slight. Okay. That a human cannot observe it, and same is for the machine, and it is classifying it as a ostrich. So it is a plenty of applications, and it has a lot of malicious applications also. We will see all those things. So we are done with the adversarial example. Now the next thing is types of adversarial attacks. How they have what are the malicious applications they have, how they can break the security of your neural network, and how basically they attack your neural network. Okay. So attacks are mainly classified into two types. If you are from cyber security department, you are aware of that attacks are basically two types, black box and a white box. And further, they are classified into two types, non-targeted attacks and targeted attacks. Okay. So in non-targeted attacks, what we have? We want our neural network to classify a image X to an iguana. Okay. But the condition is the X can't be an iguana. It can be anything apart from iguana. So that's why we are going to fool the network in a non-targeted attacks. Okay. So, okay. So in this, let's check some mathematical aspect also, how we are going to do it. So what we want y hat to equal to y iguana. Y hat is basically a prediction of the neural network, and we wanted to y iguana, and this is a one hot encode vector for a iguana. And the second thing is we have to define a loss function. In this case, we are defining the L2 loss. It is we can also use L1 loss also, but it is more better for this type of problem. And what we will do here, we start with the X can be a white noise. Okay, a noise. We will see what's the noise. Okay, data portion. So we start with a X. We forward propagate in the network. I said we have a very good network, and it is best in classifying the objects. So that's the assumption we have. Okay, so we forward propagate the image in the network, and the network computed the loss. Okay, and we backward propagate all the gradients back to the network, and this is how the optimization process works. So even after many iteration, after many times we forward propagate it, and then we will have a backward propagations, and we will use a gradient descent algorithm for the same, for optimization, and at last we will get an image that is classified as iguana. Okay. So now moving forward, so we have one question. Okay, so we have created the X. Okay, X is a white noise, this white noise you can see in the initial part. But what's the probability that will the forged image looks like an iguana? What do you think? We are the image which we are forging will look like an iguana or not? So if you think that it will looks like an iguana after the optimization process, type yes in a comment box. And if you think that it will not look like an iguana, then no. What do you think? Or anything you want? No. Yes. No. So the thing is, we have some other. there will be a certain probability. Yes, that's the right answer. We have we don't know whether the X will look like a iguana or not. It can look like an as an iguana, or it cannot be looks like an iguana. The reason behind it is that in a loss function we do not have any constraint on X that X should look like an iguana. Here you can see we have a only constraint on y hat, because that is only we want the prediction to be y iguana, one hot encode vector, and the result which we are getting for the after the optimization. So that's the basic uh, logic behind it. So now let's see, this is an iguana image, and we are working on a 32 by 32 into 3, the dimension of the image. Okay, so suppose this is a space for the possible, all the possible input images, and this is space, the red one is a space for your real images. So can you tell me, if you are using a 32 into 32 color images, then what can be the number of the possible images that can be generated? So okay, so basically in a pixel, I will give the answer. Okay, so basically for a pixel we have a 256 range, a pixel ranging from 0 to 256. Okay, so 256, and we are using a 32 into 32 into 3. 3 stand for the color channel. So the total number of the possible images we can have for the X is 10 to the power 7400, and this is same represented here. So here you can see we have a possible overlap here. Okay, we have a little bit of overlapping here. So the probability that your image relies in this area is more as compared to this. Okay, but we do have a certain probability that your image will looks like an iguana, but there is a high probability that it is not going to looks like an iguana, because we are going to land up something here. Okay, so that is the explanation. Okay, we move forward. The next is targeted attacks. Okay, so in non-targeted attacks, what we have a constraint on a y hat. Okay, and we do not have any constraint on the X. X can be anything apart from the y hat. Okay, so in this targeted attack, what we have, uh, we we have a constraint on a X as well. So in this, what we want only this watering can to be classified as crab. Okay, we don't want anything else. We just want this to classified as crab. So initially, as I told you, we have a very good network. So we forward propagate, we give it to a classifier, and if classifier is classifying it is a watering can, and it's a correct probability, correct prediction. Okay, but now what I have done, in this watering can, I added some kind of noise, the random noise, and you will get a watering, the adversarial example just like it. And if you give it to a network, then your network will classify it as a crab. Okay, with a way more probability as compared to here. It is 0.57 watering can, but here it is classifying it as a 0.91, means 91% probability that it's a crab, only by adding a certain noise. Okay, so the here we are going to see it, how it is, how it goes. So in this, we want this cat image to be classified as iguana. So this is a targeted attack because we want the same cat. Okay, so rephrasing what we want X such that y hat equal to y iguana, this thing, and X equal to X cat. So now let's define the loss function. The loss, in this loss function, we have one additional thing for the X as well, because we now have a constraint on our X as well. So lambda times X minus X cat. This is same L2 loss, but we have another term in this also. And the same way we will optimize it. We will forward propagate into a network. We calculate the loss. We calculate the gradients. We backward propagate it using a gradient descent algorithm. And after many iteration, we will find this image. What kind of image? This image. Okay. and it is classified as iguana. So that is all about the attack. So although all the above things which we have discussed is for the white box model. Here we have a network with us, and we are basically what we are doing. We have a network. We are just querying it, and using the parameters we have, we are optimizing the image. But what if your model is a black box model? Means you do not have access to it and you can't query it. Then how can you going to make an adversarial example? So if you have any guess, if you know about it, please comment down in a chat. Those who have a prior experience in against, like Rohan and Sanatan Lakshmi, I expect you to give the answer. So first tell me, is my question clear to you? Type yes if it is clear. Okay, okay. So the question is, what if the model is a black box? You cannot access it, you cannot query it. Okay. So the thing comes the transferability. So what is a transferability? Okay. So suppose if I cannot query a network and I do not have the access to its parameter, then what will I do? I will create my own network that will do the same task as the black box one. Okay. uh, and now what will I do? I will create I will forge an adversarial example on my network which I have created, and then there's a highly probability that the same adversarial image for the new network that you created uh, is a adversarial for your black box model. Okay. That is called transferability. Okay. So the only it is said that the that we use the same types of neurons, the CNN models. We use the same activation function as you see. We use ReLU, leaky ReLU, all those functions. So that is a cause of transferability. So that is all about that transferability. It is one of the research topic. Researchers are trying to find why this happens, because we forged an adversarial example for our network, and the same is going to be an adversarial, highly probability that it will be an adversarial for the black box model also. So it's tough to forge an adversarial example for a black box. As in white box, this is for the white box model. So we can query it. We have parameters with us of the model, so we can create a loss function and we can optimize it. Okay. But it is not possible in case of black box model. So now we see some of the malicious applications of the adversarial examples. What can be a malicious application? So the first is face recognition. Suppose you have a very hard security in your laboratory or something which is used your face recognition. So suppose someone create an adversarial examples for the same and break your face security system. So that can be a very malicious. Okay. And in social media we often see that if you are uploading an image that is violent in nature, and it has some sensitive content as well, so you got this type of interface. So it is said that the image is sensitive, would you like to see it or not? Okay. So what someone has forged an adversarial example for the same, and the Instagram is flooded with the violent images that contains crime and all those things. So see how malicious it can be. It can break the Instagram algorithm. That can be very hazardous for the Instagram as well, and for the users as well. And the autonomous vehicle, suppose you are driving an autonomous vehicle and somebody has forged an adversarial example for the stop sign, and your wait a second. Okay. And your vehicle is classifying the stop sign as the speed different sign apart from a stop sign that can create an accident also. And in military equipments, as we know that we have DRDO labs that uses the deep learning approaches for different type of thing. Okay, so what someone have created the adversarial example for the same, so it can hazard us in military equipment also. And in voice recognition device, suppose someone have created an adversarial voice for you, and your voice recognition device is working by the other's voice, so it is somewhere like breaking the security. So it can have a lot of malicious applications. Okay, do anyone wants to add some more adversarial examples if they can think of any? Sir, how do we know that adding a particular noise to the cat image and model it will classify? Do we label it again? Okay. So basically we are not doing the labeling. Okay. So you have this image. Okay. You give to your network, and your at initially your network is classifying it as a cat. Okay. So what you will do, you will do the optimization process. Obviously, since it is trained, it know what an cat looks like and what's an iguana look like. So we forward propagate in a network, and we computed the loss. So all we get the result. Okay, so in result you get, yeah, it's a cat. So now we want it to be classified as iguana. So what we will do, we will then back propagate all the gradients way back to the network, and we will optimize the pixels in the image. Okay, and then we will again forward propagate it, and then we again find it whether the image is cat or not. So at a certain point, when you get that it's a iguana, then your work is done. That you modified the pixel in the cat image and it is classified as iguana, you will get the probability by your network. Okay, Sanatan Lakshmi, do you got it? Okay, sir, got it. Okay, thank you. Be interactive, guys. That's way we can make this session more engaging. Okay, so these are malicious applications. There can be a lot of malicious applications. So these are the one which I can think of. So I have added in the slide. Okay. So this is the example which I have taken for the autonomous vehicle. So in a laboratory test, what the researchers do, they created an adversarial example for the stop sign. So yeah, you can see they added some kind of noise here, and here. And when they test it in a laboratory, in a stationary, when car is not running in a stationary position, the stop sign is classified as a speed limit sign. And when we are on a field drive, we are on a drive and we test it, and then it is give the same image. The stop sign is classified as a speed limit sign. So suppose you want your car need to stop, but it is not stopping, it is moving. It is what it is doing, it is limiting the speed, so it can create an accident. So that's the malicious application it has. Okay, so now the thing is, why the adversarial example exists? Do you know? Do you have some idea? Comment down no if you don't have any idea regarding the same. Okay, we got one reply. No idea, sir. Okay. So the thing is, previously researchers gives the reason that it is because of the high non-linearities in a neural network and overfitting. So basically by this, what they mean, we overfit a specific data set. Suppose we are working on a cat and dog classification, and we are classifying the cat image and a dog image. So what we will do, we will give the image a lot of cat images, a lot of dog images. So that's what they said. We overfit a specific data set and we actually don't understand what the data set is about. So that is given as one of the explanation. So after this, Ian's Goodfellow, which is basically one of the researcher who proposed the GANs also. So gave the answer that it is not because of the high non-linearities of the neural network. It is because of the linearity in a neural network. Okay, they give the mathematical explanation for the same, and this is a paper you can check if you want. Okay, explaining and harnessing adversarial examples. Okay, so let's design a method to generate adversarial example. Let's see how it is because of the linearities in neural network, how the adversarial example exists because of the linearity. So suppose this is one of the neuron we have, in which we are basically using the function, the linear regression. Okay, W transpose X plus V. It is the neuron without the activation, or you can say that the activation is X. Okay, so we give an input of X1, X2. This is the input we are giving, and we are getting the prediction Y8. So suppose we train this network, and after a successful training, we got our weights. Okay, this is the weights, and let's say the bias is 0. Okay, so for this X, this X is basically an image. So an image, and what we have done, we have encoded into a one column. Okay, flatten it down, and this is the X. Okay, the pixel value. And what we have done, we calculate the Y hat using this function, W transpose X plus V. Okay, if you know about the linear regression and all those things, so it is very easy for you to understand this mathematics. So you get a Y hat equal to -4. Now our target is to modify the X such that the Y hat changes drastically. What I mean, if I can make a little changes in a X dash such that it is approximately equal to X, and we get a different Y hat, the different value of Y hat. So how we are going to do it? So first we need to see dy hat by dx x star. It means an adversarial example. So we will differentiate it. Basically what this differentiation is telling, the impact of on Y hat of X star. There's some mistype. So it should be impact on Y hat of X star. So we got an omega transpose if you differentiate it with respect to X star. Okay. So now if you can do a little changes in an X star, it will be X plus epsilon omega transpose. Okay. It W, not omega, it is W transpose. It's a weight vector. Okay, so if I put this into this equation, this one, so we get this kind of equation. So Y hat X star will be omega transpose X star plus V, and we put the X star, our X star will be X plus epsilon omega W transpose. So W transpose, and we simplified the equation, we will get this result. Okay, now here you can see W transpose is basically W squared. So it was always a positive quantity, and epsilon, here we have a epsilon. So wait a second. Okay, so if you give a positive epsilon, epsilon is a very small quantity. So if you give a positive epsilon, your Y hat will go in a increases in a direction, in a positive direction, and if you give a negative epsilon, your Y hat will be less. Okay, so in this example what we have done, we have taken the epsilon equal to 0.2, and we created an adversarial thing, the adversarial example for the same, and we get Y hat extra equal to 1.6. So you can see that on small changes in an X, it's a 0.2% of all those things. All 0.2% is very slight, just 1.02. Here we are basically 3.06. Okay, so basically we are just changing the weights, the X by only a smallest quantity, and we are large, and we get some different y hat. Here we are getting -4, and here we are getting 1.6. So it basically changes the input. So now the thing is, if you will see this equation, then if W is very large, suppose it has very bigger quantity, then if your epsilon is smaller also, like 0.1, suppose W is 2000, then a 200 pixel can be a value change can be very much, and it can change the X. So if W is very large, X star can't be approximately equal to X. X star is basically the adversarial example, but we need, as we need the same, we need that X star is approximately equal to X, but since W is very bigger, we cannot do it. So researchers, what they gave, they said that instead of using the W transpose, what we will use the sine of omega. And if we use the sine of omega, then we can push in a desired direction what we want. Okay. So this is all that thing, and and due to this explanation, we will have fast gradient sine method, that is for the neural network. Now many of you are thinking this is for the linear network, we are using the linear regression, then why it is happening for a neural network, as neural network is one of the non-linear network. Okay, so the thing is, we are basically moving forward in making the neural network linear. We use the ReLU activation. If you know, then ReLU activation is basically a linear activation function. Okay, and we are using various kernel initializer. So basically they are basically what we are doing, we are just making the neural network into a linear design, and that's way we are making them to train faster. Okay, so what researchers do, the above explanation, they use this equation for the neural network. So here instead we are using the gradients, the gradients of the loss function with respect to y level, the sign of it, and forging the adversarial example. It's okay if you do not understand the mathematics much, but you should aware that it is basically taking the sign of gradient. FGSM is taking the sign of gradient to create the adversarial example, and it is one of the fastest what you can say, faster adversarial creating method. This is the fastest way by which you can create the adversarial examples. Okay, so this is the original image, and we calculate we calculate the pixel value and corresponding what we want. We need to increase the pixel more or less depending upon the output of the gradients of the loss function, and we get this adversarial image. Okay, and this is a tiger with a 20% confidence, and the same tiger is classified as tiger cat with a 30.6 confidence. So you guys should know about the tiger cat. Okay, tiger cat is very far different from the tiger. So FGSM, I already told you how it works. It take your input image, it make the prediction using the CNN, it computed the loss and their gradient, and using the sign of gradient, we are going to force the network. So there are several others adversarial attacks also. So since FGSM is one of the fastest methods, so we have covered it. We are not going to cover these four. These are little complex and do have some a great mathematical explanation for the same. Okay, IFGSM, deep fool, GSMA, all these are the way to create the adversarial examples. Okay, we are. Is the screen visible to you guys? The Chrome screen?
Yes, sir.
Okay. So here you can see this is just a code for the adversarial FGSM. Can you see it? Okay. So initially, this is a dog which is classified we are classifying the breed of the dog. So it is saying it's a Labrador. It is also known as Lab with a 41.82% confidence. So then we do the same thing. We use the FGSM technique and we created these 4 and 5 different type of adversarial examples. So here the epsilon is 0.10. You're seeing how less it is, 0.10 only. And the same dog is classified as Saluki. Saluki is a different breed of the dog, but a lot of difference is there in between the Lab and the Saluki. And if we increase the epsilon more, it is giving you some different breed of the dog. Okay. And if you are using, if you are increasing the epsilon 0.150, then it is again giving you the same. So this is how we are forging the adversarial example using the FGSM. So now, since we have an attack, you have a neural network and you are using it in a production, and the attackers are trying to attack your neural network. So by creating some of the adversarial example, but the thing is, how will you going to defend it? You need some kind of defense, right? Defense is very important. Okay, so there can be many number of ways to defend the model. There's no any ultimate way to defend us, which defend us from the adversarial attacks. And attackers are basically generating new types of attack. If you belongs to a cybersecurity field, then you are quite aware of that we are going to have different kind of attack. Different. Is there any relation between epsilon and confidence? As epsilon increases, confidence increases. Okay. We cannot say whether as epsilon increases, the confidence increases. But obviously, suppose this is the field and you are here, okay? And this is basically the boundary for the tiger. So I cannot able to write, I do not have canvas. So you calculate the gradient and you move it in a positive direction, then you will get here. So then you will come in a boundary of tiger cat. So if you are decreasing the x, then you can come here. So we cannot say whether it will affect the percentage confidence. You need to check it. And we do have a different type of attacks also, adversarial attacks also. So I hope I give the answer to you. Okay. So talking about the defenses, we have I have taken 3 type of defenses. So first is create a safety net. So what we will do, you have a neural network, you will create another neural network, and which will check whether the image is adversarial or not adversarial, means the image is real or fake. And after that, you pass it to the neural network, which are basically classifying classifying what you want. Okay, so now you can also say that sir, we can make an adversarial example for fooling the safety net also. Obviously you can do it, and there's a highly probability that you break the safety net also. But the thing is, fooling 2 network at the same time is difficult task as compared to 1. Okay, so now the second is train on correctly labeled adversarial examples. So what we have, what we do, we have suppose we get to know that this adversarial example for our network, and what we do, we label it and we train it. Okay, and the third is adversarial training. This method is very costly. You need to forge a lot of adversarial example, then you will label it, then you will train it. And the third is adversarial training, in which whenever you are doing the training of your neural network, you are creating simultaneously you are creating the adversarial examples using these different type of techniques. Suppose if you are using FGSM, so at the same time you are using the FGSM to create the images, and you are training your network on this. So this is pretty much favorable, and it depends on a type of attack also. So we can have many more defenses which are far better than all those three. You can check this research paper if you are interested. Defending against adversarial attacks toward deep neural network via collaterability task training. We will share this PPT after the session, so you can find the link here. There's another research paper. Adversarial examples are not works; they are features. So as I already told you, a lot of research is going on GANs. So we will see, and these are all the part of the GANs, because GANs are the second thing. First, you should know about what are the adversarial examples, attacks, and defenses. A basic knowledge of all these things is necessary. Okay. So now the first portion is completed. We have seen the adversarial examples, attacks, and now we are moving forward to generative models. So if you have any doubt regarding the first portion, let me know, because we are moving forward to a generative models. So you can type yes and no. No doubts. Okay. And by the way, you can use the FGSM for creating the adversarial example for your own image also. If you or anything you want, like a bag or anything you want. So did you send? Please don't direct message me. You can message to all. Okay. It is very easy. You can find the code on the internet, the FGSM, and you can create a lot of adversarial examples and fool your network if you have created any of the CNN. Okay. So now we are talking about the generative models. In short, generative models is basically used to generate the data set. So we can generate new data. So the new data can be images also. The new data can be audio also, text also. There can be many things we can generate. So basically they are used for generate different type of data. Okay. So before moving to a generative network, we will see what we basically using before the generative, what we basically use in a day-to-day life. So we will use we use the discriminative models. So discriminative models, also known as a classifier, which is basically good in classifying uh, the object, whether it's a cat or dog. So suppose so this is the classifier which is good in classifying the dogs and cats. I hope you guys have worked on a CNN also for a classification purpose. So that is a discriminative model. Okay. So basically what it does, you give the feature X and you predict a class Y. And in the mathematics term, it is called as a conditional probability of Y with respect to X. Okay. And for the generative models are for generating the images. So suppose here we generated a dog images. So for in this case, we will give a noise X and we will give a label Y. What we want to generate dogs. Okay. And it will create a dog image of the dog for you. Okay. And it is given by the conditional probability of X with respect to Y. Basically it is telling what's the probability of X when Y is given. Basically you will give that label, right? Okay. So these are the some of the images that is created by the GANs. So you can see the dog image. This dog image is created using the GAN. We will have a DCGAN implementation at the end of the session, in which we will generate some of the new images. Okay. So here you can see this is a GAN used for a face generation task. Here you can see the one thing I would like to told you that these person do not exist in a real life. Okay, so it is all created using GANs. Wait a second, guys. Am I audible to you guys? Sorry for the interruption. Am I audible to you? Hello? Please type in a chat box if I am audible. Okay. So these all the images are generated using GANs. We have very more interesting applications of the GANs. Okay, we will see all of them. So now let's talk about the generative models. So we have basically two type of there's many type of generative models. In this we are basically going to talk about VAEs. So we are basically going to talk about VAEs and GANs. Okay, so we will briefly talk about VAEs and our more emphasis will be on GANs. So in VAEs, what we have an encoder. What does encoder do? We give an image. Suppose this is the image 1, 2, 3. We flatten it down and we give it to a encoder, and the encoder job is to encode this image in the latent space. Okay, and then we will have a decoder. What it will do? Suppose we encoded the image here. Okay, and what will our decoder will do? It will take labels from the data from the latent space and will try to create an image. So encoder job is to is initially we do not use the encoder after we encode all the images to a latent space. So this is an auto encoder. Okay, so in variable auto encoder, what we have, we encode the image with a probability distribution. Okay, complete probability distribution, and then we take all those things. And in GANs, what we have a generator and we have a discriminator. Both generator and discriminator will fight against each other. Generator will try to fool the discriminator and discriminator will try not to be fooled. And that's how a training goes on. So in GANs, what we give a random noise. We give it to a generator. The generator generate the images. Okay. So we will now going to talk about mainly talking about the GANs in detail. Okay. So as I told you, GANs are the generative models used for a unsupervised learning proposed by Ian Goodfellow in 2014. So it consists of the two networks, a generator and a discriminator. Generator work is to generate new adversarial images. Discriminator is to discriminate whether the image is real or it is fake. Okay. So what I mean by fake, if the image is generated using a generator, then it is going to be labeled as fake for the discriminator. Okay. So both the network completes against each other, and we get our generator trained. We will see all those things. Okay. So now let's see the probability distribution. So these are the images we sample from the real world distribution. And when we encode these images in a 2D dimension space, we have this kind of representation. So this is a probability distribution of all those images. And suppose, wait a second. and suppose we have taken some of the images from generated distribution. Okay, so these are the images from the TO GANs. Okay, and we plot its probability in a 2D map, and we will find such kind of probability distribution. So our basic job is to match the distribution of the generator with a real data distribution. So that is our goal. So if we can do it, if we get the real world distribution probability like a real world distribution, then we can say yes, your generator has a good ability to generate new images. So basically this is a generator network, and you give a noise. As I told you, you need to give a noise to the generator, and it generate some kind of random images because initially it is not trained. So we get some kind of random noise here. Okay, so now we want some real images now, but we get some different noise because it is not trained. So we need to train it. So how we are going to train from the true data distribution? So that is the thing. So now we are moving forward in a training procedure of the GANs. So first I will let you know that GANs are very hard to train. Often I simplified it, the way to train it. I will explain it from the scratch. Okay, so this is the generator network. Okay, you give a noise, and initially generator gives you a random noise. Okay, so now you want it to train. So what we will do, we will have some real images, real data set, and we will have a discriminator. So we will give the real images and the generated images to the discriminator, and our discriminator will classify by equal to 0 if it is comes from generator, and by equal to 1 if it is coming from discriminator. So all the images under the real data distribution will be labeled as 1 because they are real, and all the images the generator will generate will be labeled as 0. Okay, so now how the training procedure works. So we calculate the loss and all loss, and we calculate the gradient, and then what we will do, we will backward propagate the gradient all the way back to the generator network. So suppose if your generator generate this kind of images, and it said and you give it to a discriminator, and discriminator said yes, it is by equal to 0, means it's a generated image, the discriminator is able to classify. So we will back propagate all the gradients to the generator, and generator will try hard to generate a kind of images so that discriminator can be fooled. So this optimization process works, and at the end we get the images uh, 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 to be a real when our discriminator will not able to classify whether the image is from generator and discriminator. So what will be a condition when discriminator will not able to distinguish whether the generator whether it's a generated image or a real image? So when it will give you the probability of 0.5 or something like that, so you will say yes, that discriminator is not able to distinguish whether it's a generated image and the real image. So that is how the training goes on. Okay, if you have any doubt, you can ask, because we are moving to a mathematical explanation for the same. And this is the optimization process, the way we back propagate the gradient all the way back to the generator, and generator will then modify the pixel in an image, and the generated image will then again fed up into a discriminator. The thing is, discriminator is also important, guys. If your discriminator is not good, if it is not good in classifying the generated image, the real image, then you can't able to learn. We will see it also. Okay, so now I guess no one has any doubt, so we will move forward a training procedure, how we can train against. So what will be a cost of the discriminator, guys? You can tell me this, because use the CNN network. So what is the loss function you use in a basic CNN network? Type no if you can't able to remember it. Like obviously you guys have created some of the CNN network also, and you uses a cost function, and that cost function has a name. So I'm just asking you the name. Yes. Yeah. So we got the answer. We are using the cross entropy. So since we are working on a binary classification, we will use a binary cross entropy loss, and this is how an a cost of the cost function of the discriminator looks like. Okay, so there is a slight difference in the from the regular binary cross entropy, that since all the images from the real distribution is labeled as 1, so we do not have any fake images in a real data set. So basically this term is saying that these should correctly label real data as 1. Okay, and here apart from using on a real data set, we are using it on a generated data set, and this term is saying that these should correctly label generated image as 0, because what we want discriminator to classify whether the image is generated or real. So that is the cost of the discriminator. Okay, so now see the cost function of the generator. Would you like to guess what could be a cost of the discriminator? Take some random guess. It is related to the cost of discriminator, because what we want what our discriminator is doing. We just want the opposite the discriminator is doing. So if discriminator is classifying the generated image as 0, what we want the same generated image to be labeled as 1. Yeah, it is cross entropy. Yeah, you can say it. It's a bit complicated. So it's basically a cross entropy loss. Obviously, this loss we are going to use. But here, what we have, since we are not going to pass any real images in a generator, we are working on a generated image. So y real will be 0 in this case for the generator. Okay, and we will left with this only, this term. So you can see. But the thing is, since it is this term is used full 0 when the label is generated. So what we will do, we just do the put a negative sign here. Okay, so by using a negative sign, what we are doing, we are now doing the opposite case. So here G is trying to fool the D, and I hope you guys got the intuition here. What we are doing, D is classifying the generated data as 0, but here we want the opposite thing. So we want that discriminator to classify it as a 1. So that's a loss function we are going to use, just opposite of the discriminator, because we want the opposite thing to happen. Okay, so now this is the one type of way we can train the network, but often we see that this loss function doesn't work good. Okay, because okay, we will see it in this graph. So suppose this is the discriminator output of your generated images. So initially discriminator, if it's a fake image, discriminator will say it's give 0, and if the discriminator get fooled, then it will say it's a 1. Okay, then often this is a saturating cost. Okay, so here you can see in this region we have very small gradients. Okay, so it will initially our generator is also not good in generating that data set, so we will be somewhere here, and in this region we are seeing that the gradients, I'm talking about the saturating cost, which we have talked about earlier in our previous slide. Okay, So in this region, you can see the gradient are very small. And if you have a very small gradient, you cannot train uh, uh, effectively. So what we have done, we created a non-saturating cost for the same. What we have did, we just did a mathematical transformation for the same. So we need to minimize this thing. Okay, what we have done, we have this is a mathematical thing. You need to if you are minimizing it, then it is same as maximizing log of d of g of z. G of z is an image generated by the generator, and we are feeding it to a discriminator. Okay, and then if you are using the minus sign, then you will use the minimum. Okay, so your max will convert it into a minimum because we use a negative sign. So this is how a graph looks like, and here you can see at the initial reason we do have some gradients. It is not zero, just like in this case we have a small gradients, but here we do have the gradient, and that's why we use this kind of loss that is called as a non-saturating cost, and it is more effective as compared to this saturating cost if we are going to train the GANs. So these are two methods I have discussed. One, you can use the saturating cost for training the GANs, and another method is non-saturating cost. Okay, so what do you think, which network is difficult to train, generator or discriminator? Type something in a chat box. Generator. Okay. Anybody is here who is thinking that it is tough to train the discriminator as compared to generator? You can type yes and no. Okay, so although we got our answer, the answer is generator. Obviously, if I give you an image and say classify, tell whether the image is cat and dog, then you can say it in a second, yes, it's a cat. But if I give you a blank paper and ask you to draw an image, then it's a very tough task. And the same is applied to the generative adversarial network. So uh, generator is very tough to train as compared to discriminator. So now question is, which one is most important to train the GANs? Discriminator and generator. Option will be same. Think guys, which one is most important network to train the GANs, whether it's a discriminator or a generator? Okay, we got one answer, discriminator. Okay, let not waste much time. Okay, so the answer is obviously the discriminator, because if your discriminator is not able to distinguish whether the image is real or generated, then how will you train your generator? Okay, so discriminator is most important, and the thing is you cannot have a very good discriminator at the starting. What you need to do, you need to simultaneously train the network, guys. That's how both the network, that how you can progressively train the GANs. So this is the most important thing. Okay, so as I already told you, discriminator is more important, because if you cannot able to distinguish whether it's a real image or the fake image, then there's no any way you can train the generator. Okay, so what we will do, this is another hack for the problem. So what we can use for the number of epochs, we use the k iteration for training the d, and only one iteration for training the generator. So this is how our discriminator will be the schemata will be better. Okay, and this is how we can progressively train the network. Okay, so let's talk about different type of gain: gain, NS gain, W gain, min max gain. So we have talked about these two initial, the min max gain, and we use this kind of loss function here. And for the generator loss, we use a saturating cost. So, and for the for this gain, we non-saturating gains, we use this log of dx. Here we are using log of 1 minus dx, and these both are same. And we can have another type of gain which are using different types of loss function in order to improve the result. You can check this paper. It is one of the best paper we do have for the comparisons of the gains, that our gains created equal a large scale study for the same. Okay, so here you can see the explosive growth in gains in 2014. Jan's Goodfellow give one research paper, and in the recent year, in 2015, 16, 17, 18, we have an explosive growth that is called as exponential growth. Okay, a one research paper give birth to hundreds of research paper, and it is also one of the hottest research topic nowadays as well. And since I have a data of up to 2018, there's many more research publications in 2019, 20, and 21, and researchers are trying hard to train GANs more better and efficiently, and many more things, and to make GANs to put in our industrial uses. Okay, so moving forward, we will see some of the real life interesting applications of the GANs. So this is the first paper titled in 2017, progressive growing of the GANs for quality, stability, and variation. So in this paper, they generated the human faces. I already told you, and this is how the examples look like. Okay, these are all the realistic images of the humans, and you can see, and these do not exist in a real world, guys. These are all generated by the GANs. Okay, so you can see the tweet of the Jan's Goodfellow. He wrote 4.5 year of GAN progress on a face generation. So when we are in a year 2014, we are only able to generate the black and white images, but you can see the progress, and here you can see we are generating the realistic image just like the real human. This is generated by the GANs, and these are the paper titled for the same. Okay, and these are another operation on codes, in which we give a noise vector, we generate an image of a man with a googles, and we give another noise vector, and we get another image of the man, and we give a third noise, and we get an image of a woman. So what we have done, we have subtracted code 1 from code 2 and added code 3. So if you give it to a generator, then what you will get? You will get a woman wearing the sunglasses. Okay, so basically the face is subtracted, the human face is subtracted. So that's one of the pretty interesting applications on GANs. And now we have image to image translation in a GANs. What you can do with a GANs? So you can this is a segmentation image, and you can create into a real output. This is a label, and you can create it to a facade building. Okay, you can create you can convert the black and white image with a color. You can fill the color in a black and white image. Okay, using the GANs. You can convert the satellite image to the map image, and the map image to the satellite image you can convert day to night, night to day, and you can convert this type of thing, sketch into a complete object. And there's a lot of applications of the GANs. If you have seen the Harry Potter, then there's a moving portrait in a Hogwarts. So you can also generate it using GANs. So it's pretty interesting. So here we are. So these are some another applications in which we are unpaired image to image translation using cycle consistent adversarial networks. So in which we are classifying and monet into a photo, basically a painting into a realistic photo, zebras to horses, summer to winter, and a lot more, a photograph to drawing. So these are coolest application of the GANs. And basically industry, we will see all the industrial applications also. So this is one of the industrial application in which we are using the SR gain to increase the quality of a low resolution pic. So we have a low resolution pic. It is not given here. We give it to a network, and we perform a bicubic interpolation. So if you have attended my live session on a OpenCV, so a bicubic interpolation doesn't work that good. The image quality decreases. But if you use the SR gains, then you will get this type of image. And this is the original high quality, and this is the high quality image we have, okay, for the low resolution image which we will give. And we can check out the similarities between the two. SR gain has created a good job, has done a good job for increasing the resolution. And the paper also titled SR ResNet, which are basically not using the GANs, but using a CNN approach. So the result, but the SR gain is state of the art, okay, for a super resolution. Also, we nowadays we do have diffusion models also for super resolution, and they are beating the SR gains also. So all the things are going very fastly. Research is going very fastly. People are generating new and new techniques each day. So here you can see this is the low resolution image, and using the SR gain we get this kind of high resolution image. And this is the real high resolution image for the same person. You can find the similarities. Although there's a little this noise here, you can see it is not as smooth, but it done a very good job. Okay. Now you can use the face generation. So I'm playing a YouTube video, so you can see in this video, they researchers try to give you how they created the face. Let's move forward. So this is a source A and this is a source B. So they try to combine it, and by the GANs they try to see it. That's the result how they got. This is using the GANs, okay. Now here what they have done, they have taken the three images and tried to combine it, and they will see how an image looks like after they give it to a GAN. So here you can see basically these two images are fixed, and they are changing the first images, and they are getting the different results. And And this is a case when we give a noise vector to a generator, and generator is giving you this kind of image. And what we are basically doing, we are just increasing and decreasing the noise strength, and as a result we can see how the image changes. We have created different researchers created different GAN for different purposes. In this, they are changing the style scale. This is a style scale. This car is stationary, and using the GANs, they have made it to moving. Just like I said, that you can create, yeah, just like in a Hogwarts, the image portrait is moving. You can create that one also. NVIDIA is doing very well in terms of GANs. They are designing new algorithms, and Apple and Facebook researchers are also working in basically the GANs. And nowadays we are also uh, working on GCNs. If you know about it, graph convolution neural network. These are one of the hottest topic in the industry for the research and for the industrial uses as well. Okay. Okay. So now this is another website. We are going to check it also. So here, this is the website created by Christopher Hesse, and what he have done, he has used the GAN. So if you are give the edges, then it will create it will give you a real cat by using the in edges also. So that is he named it as edge to cat GANs. Okay, so let's clear and let's try to. Although I'm not a good drawing, but let's see what we got. These are the random they gives, and this kind of image we got. And you give the this kind of thing, and you will get this edge to SUSEs. You need to train for a specific data set, and then it will create the thing from the edges to the real output. Yeah, he created the portrait uh, using by his mouse, and he created the bag. You can see it look. So I don't know how it looks, this kind of bag. Okay, so that is one of the applications which we have in GANs. So there's another many other applications: text to image translation, semantic image to photo translation, generate new human poses, photos to emojis. You can convert photo to emojis, emojis to photos, photos in painting, video prediction, etc. So give me a second. I'm Okay, not an issue. I was not able to find that application. We will move forward. So now my question is, GANs are what do you think? GANs are supervised or unsupervised? Type in a chat box. Take a guess. Supervised. That's a very good question. And if you understand the proper working, then you can easily answer it. Semi-supervised. Unsupervised. Okay. So the answer is they are considered as a unsupervised. They are considered, although they have some kind of supervised. So as Rohan said, it's a semi-supervised. So obviously, we do have unsupervised supervised loss. So GANs are basically classified as an unsupervised algorithm which which has a supervised loss in it. Okay, so in general, we term it as an unsupervised, but although they are semi-supervised. So did you send any feedback from attendance? Okay, so there are few company listed here which is using the GANs. The Adobe is using for the next generation Photoshop, and Google is using for the text generation. For how Adobe is using, suppose you give an image, suppose uh, I remember one of the startup in which what the startup is doing. The startup is creating the models using the GANs, and basically they are uh, uh, doing the advertisement. They are using the same model for their uh, for promoting their products. Okay, so that is one of the applications as well. IBM is using for the data augmentation, and we do have Snapchat and TikTok. They use the filter, how the filter works. So we can also they are using the GANs for the same. Disney are using for the super resolution. As I told you, super resolution is one of the good application of the GANs, and data augmentation is one of the best applications of the GANs. We can create a lot of data if we have a less amount of data. Then using our GANs, we can we can create a lot of bigger data set. And this is only a 5 big companies. There's a lot of company are using the GANs, and I see a lot of startup to using the GANs for the training purpose, for their different purposes. Okay, so this is all about the PPT. Now we are so if you have any doubt, ask me regarding the GANs, since we are moving forward to our implementation part. Type yes if you have any doubt, or you want to ask something that you don't find the answer, and you can ask whatever you want regarding the applications in the industry. Clear, sir? Okay, now then we will move to implementation part of a DC GAN. Can you see the Jupyter notebook? Type yes. Can you okay. So I have taken the I am implementing a DC GAN. Wait a second. So I have implemented a DC GAN, and what I'm trying to do, I am trying to create the digits. I am working on a MNIST data set. Okay, the same notebook you can use for creating the human face also, but in that case you need to change the data set. You need to change the data set to the human faces. Okay, so first we imported the libraries which we need, TensorFlow, that is in which we are going to do all the training and all those things, and NumPy, Pandas for the pre-processing thing, and Matplotlib, and these are the supportive functions, OS and time for calculating the time, Matplotlib for plotting the plots and plotting these images also. So we load the MNIST data set can be loaded using the keras.dataset.mnist. So this is how we load the MNIST data set. Okay, and let's see the number of images we have in a string, because we don't want to test anything. We just want an image for a discriminator that is real. So we do not bother about the by train also and by test also. We are going to label all it as a 1, as they are the real images, and the generated images will be labeled as 0, as I already told you. So we have 60,000 images which has dimension of 28 into 28, and this 1 stands for a grayscale, since these are the grayscale images. This is a function to plt.imshow basically, and a loop over those functions so that we can get a plot, and you can find these kind of digit we have in the real data distribution, real data. Okay, 5, 0, 4, 1, 9, 2, 1, 3, 1. Okay, so what we will do, we need to, since this data is loaded from the MNIST data set, the keras one, it is already in a form of tensor, but sometimes it is not in a form of tensor, and for giving to a CNN network, you have to convert, reshape the data in a form of tensor. So this is how we are going to do it, and this is the method to normalize the images. So we are basically normalizing it to a -1 to 1 range. You can also use X train divided by 255 to normalize it to a 0 and 1. This is a basic CNN thing. Okay, the image processing thing which we do. Now let's say we have 60,000 examples, and the best size I am taking 256. So I need to take the data in a batches. So I will take the help of the data set from tensor slices, the function which we have in a tf.data.dataset from tensor underscore slices. So we get the data extrain, and what we will do, we will shuffle the data and in a batch. So at a one point we are only taking 256 images for a one pass. Okay, so the thing is, if you are working on a CNN, then you are aware that CNN basically downsample your images. The convolutional layer basically downsample your images. But in Generative, what we wanted to input a real images. Here you can see we downsample the images. We have a bigger image, we downsample it using the convolutional operation, and here also, and we check whether it's a real or fake. But in Generative, what we want, we give a random noise, we want to upsample it so that we can get the image. So this thing can be implemented using the function convolutional the layer convolution 2D transpose. Basically, in a discriminator, we use the convo 2D layer, and for downsampling, and for the upsampling, you need to use the convolution 2D transpose. So this is the generator model. I use the keras sequential API to create the model. Every one of you are familiar of this, as it's a basic thing. So what we have done, we have created a dense layer in which we are inputting the noise of a noise vector of 100 dimension. We are inputting it into a layer which is dense, and we are basically using the size 7 into 7 into 256. 256 goes for the channels. Okay, then we add the batch normalization to normalize to basically learn faster and to normalize the batch, and at the last we use the leaky ReLU. Okay, so in general, we can use a leaky ReLU before the batch normalization, but in case of leaky ReLU layer, we often use batch normalization before the leaky ReLU. Okay, and now I have reshaped the image into a 7. This is very necessary because I'm going to fed it in another layer. So in the another layer, I have created another convolutional 2D transpose in which we have a the size will be 128 and 5 into 5 will be the kernel size, and the stride is 1 into 1. Padding will be same. What does it means? That we will have this is number of the filters, okay guys, and padding will be same. What does it mean? That the input image, so you are inputting an image of 7 into 7 and you will get the 7 into 7 same output from this layer. Okay, and this is the best normalization again, and activation function leaky ReLU. So this is another convolutional 2D transpose layer in which we are using the number of filter 64, and filter size will be 5 into 5 and the stride will be 2. So since we are using the convolutional transpose and padding are same, the 7 by 7 image will be become 14 into 14 since we are using the strides of 2 by 2. Okay, so same thing, batch normalization, leaky ReLU, and then at the end we use the another convolutional 2D transpose layer with a filter of 1, and since we want to give a grayscale image to the discriminator, since our discriminator will be trained on a grayscale image, so that is very necessary, and we will take the stride of 2, and so our 14 into 14 images will turn into a 28 into 28 images. Okay, why there's necessary that we created the image of the dimension 28 into 28 using the generator, because we are using that 28 into 28 dimension images for training the discriminator as well. So that's a necessary. And at the end, we are using the 10h function here. The main reason behind not using the leaky ReLU, because if you are using the 10h function, then it will give you the range from -1 to 1. And in case of, as I already told you, that we normalize the image where it is in range of -1 to 1, then it will come from the same probability. The probability will be same, the pixels probability. Okay, so that's why we use a 10h function. If you use 0 to 1, if you just do extend divided by 255, then the image will be normalized in range of 0 to 1, and then you can use a sigmoid here also, or obviously you can use the ReLU function also. Okay, so this is all the generator architecture. We call the function generator underscore model and print the summary. So this is a summary, and the number of parameters we have, the number of layer we have. Okay, now the thing is noise, so we need to generate. Let's try this generator. Okay, so initially it is not trained. Okay, so what we have generated a noise, random noise, which is a column vector which contains 100 of the 100 rows. Okay, a single column which contain 100 pixels. Okay, and we give it to a generator. So as I told you, generator is not trained initially, so the generator output this kind of images. So obviously this is nothing, this is just a white noise we have. So we need to train the generator. For training the generator, we want a discriminator. So now let's move forward to a discriminator. So as I already told you, discriminator job is to basically in discriminator we do downsampling of the images. So we will use the convolutional 2D layer. So this is again you should be familiar of. You initialize with tf.keras.sequential. You add the convolutional layer with 64 filter and 128, and the input size is 28 into 28 into 1. If you are taking some different input, then you need to change it here, and you need to change the generated dimension using some different strides also. And then you add a leaky ReLU, you add a dropout layer. You guys are familiar of that, I know. You should have to. Okay, So at the last we use a flattening layer and the dense layer at the end. So the dense layer will give you the in a dense layer we are using the only one neuron, so it will be a output layer which will give you the probability whether the image is real or a fake. Okay, so now we call the function and we get the discriminator. So this is how this is a summary of the discriminator. Okay, so now let's define the discriminator loss. So discriminator loss contains of two things I told you: the real loss and the fake loss. Real loss is for the discriminator should correctly identify the real images as one. So this is how a cross entropy loss, in which the uh, we try to. This is how this thing is telling that your discriminator is classifying uh, uh, the real image as one, and the fake loss is tf dot underscore zero like dot fake output dot comma fake output. So this is telling whether your the generated image will be a 0. Okay, so the total loss will be a real loss and fake loss. I already talked about these things, the losses, so I'm not going to take it here. And this is how we are going to generate it. Okay, and same for the generator loss. You need to copy these things, but here instead of real output you will be saying the fake output, because what you want your discriminator to fool. Okay, so this is a generator loss. Okay, so since we have two neural network, we need to have two different optimizers. So we are using two different optimizers. The Adam, although we are using the same, but we have to initialize two different Adams optimizers. And this is for the discriminator. We are passing the learning rate 10 to the power minus 4. So this is basically a checkpoint. The way to checkpoint the network. Suppose if your network if you have some network issue or something, that it will checkpoint help in checkpointing well the training. Okay, so the number of epochs I am using 50, the noise dimension I am using the 100, and the number of example to generate I am using 16. So basically this is a seed, this is a noises we have. Okay, this will help you to save the examples also. We will see how. So this is a custom training loop. Okay, so in general what you guys use, you use the model.training API. Okay, but here we are using the custom training loop. So first we need to initialize at tf.function. This function help you to compile the function. Okay, so it is mandatory before proceeding. So we design a custom training loop. Okay, so this is a noise vector tf.random. So we are taking the normal values, any from the normal distribution. The best size will be, I already told you, and the noise dimension I will be taking 100. So we will get a matrix of the noise. So a gradient tape help you to auto differentiate the gradients. Okay, so we do need to have different gradients for the generator as well as for the discriminator. So generated image will be, we generate the image. Okay, here we call the generator and we give a noise, we generate the image. The real output will be the images that come from the real images, it considers the real output, and the fake output will be the images comes from the generator. A generator is considered as a fake output. Okay, so the loss I call the loss function. So in generator loss we only need to give fake output. As I already told you, we do not bother about the real thing. Okay, and in discriminator you need to give the real output and the fake output as well. So basically how you calculate the gradients. So this is how you are going to calculate it. GAN tape, the gradient tape which we used, dot gradient. So we give the loss and the generated trainable variables. So if you are aware of the working of the neural network, then it is very easy for you to understand all those things. We are just trying to calculate the gradient of the loss function with respect to the trainable variables, and we are at the last, and same for the discriminator. Okay, and at the last what we are doing, we are applying these gradient into the optimizer so that your optimizer can work and minimize the loss. So this is a custom training loop. Although you can also use the model.training API, the method model.training, which we have in a Keras. But since most of the internet example, you will see this kind of thing because it is very easy to train, okay, by this way instead of using that. So you should aware of this thing. And here the thing is you can take different type of losses and all those things. You can check the gradients for all the layers, but in that case you do not have that much of the access to your network. So this is a training loop. For the 15 loops, I train the epochs is 50. So for train image in a data set, I train step is basically this function. I give the image batch, first batch of the images, and the training procedure begins. Okay. So the display, this is the function to display and save the generated image. And this is a function to checkpoint the training in every 50 seconds. Okay. So this is a function to generate and save images. Here we call the function. Here you can see, and this is how we are going to show and train. So after the 15 epochs, we will get, if you train for a 15 epochs, we will get this kind of generated images. Okay. Here you can see we get this is 9. Although these are not good, you need to train on far more epochs. Okay. So now I'm just training the thing in front of you guys so that you can visualize. It will take some time. Okay. You will see how the generator will generate the images. We will call all the function. So these are 15 epochs. We hardly, it will take just 5 minutes and it will converge to a 15 epochs. Okay. If you train it to a more number of epochs, let's say 100 and 150, then you can get better results also. Maybe I guess my internet is some issues, so it is taking some time. Okay, we can see the training procedure begins. So every epoch that the generated image will be visible to you here. So initially you can see generator is randomly giving anything. These are not the digits. So 15 seconds for one epoch, and you have almost 15 seconds for the second epoch also. And you will see the progress of the generator. So it is almost it is the end of the today's session, guys. So let's wait for it convergence. Until if you do have any doubt, you can ask me. You can ask the question in a comment in a chat box if you have any doubt. And if you do not have any doubt, then please say no, you don't have any doubt. GANs are one of the advanced topic, and it is very difficult to digest all of the thing I told you. And there's a lot of many ways to train the GANs. And I already told you GANs are hard to train. So yeah, you can see your model start learning the things. Here it is generating the 3, although it is not that good. and the generated image will be saved in the in a same directory. So that's all. You can see the working here, and I already told you how the image looks like after 15 epochs. We can wait if you want till it converges to a 15 epochs. So I'm concluding the session here because if you proceed with the training, it will almost take about 8 minutes of the training. We will share the code and you can train it for far more number of epochs at your PC. I'm not taking your much more time. So that's all. I'm stopping the session here.
Thank you so much, Ansh, for such a wonderful session. Gains are really, really important, highly important if you want to sustain in data science field for a long time. Applications of gains are really immense. You guys have seen what Ansh has presented. And there are lots of research papers that are being submitted on GANs like almost every year. So before we wrap up this session, I'll request you all to provide your feedback on the link that I'll be sharing right now. Okay, so what we are doing is you have to say a word, okay, one word. How do you feel about the session? It could be positive, negative, whatever you feel. If you think, okay, it was really good, please do mention, one word. How would you like to summarize the whole session in one word? Okay, either it's positive or negative. However, the elaborative feedback would be taken later on. If you guys follow me, could you please type yes in the chat window? Can I have responses from the people? I know, today's session strength is a bit low, very low in fact, compared to our last live sessions. Do you guys follow me? Like, could you guys provide feedback in one word on the mentioned link? Can you type in the chat window yes, no? Okay, so now let me say yes. Okay, and make sure that you guys submit or mark your attendance on the mentioned links I have shared already. If you guys haven't got the link already, I'm sharing it once again. So it will help us identifying, who has attended the session, and we can release the participation certificate accordingly. I have reshared the attendance link. Please mark your attendance and please do provide your one word feedback on the link that I have shared. If there is any doubt about this session or about anything that you would like to discuss to the Ansh or to me maybe, please feel free to unmute yourself and ask the doubt. Today's live session strength is really low compared to previous live sessions that we have attended, that you guys have attended. Right. So if you guys do not have any doubt, please say no in the chat window so we can wrap up the call. And if there are any doubt, please do unmute yourself and ask it out. Can we have responses, please? I see there are only 7 participants. Can any one of you say no doubt? If there are any doubt, please ask it out. No doubt. Lakshmi says, okay. Okay, then I take that as a a collective okay answer. Okay, Anushka says no doubt. Okay, thank you so much, guys. Have a wonderful evening ahead. Happy weekend. Good night. Take care. We wrap up the session for tonight. Thank you so much.